Nuclei. Let's learn about isotopes, isobars, isotones, nuclear size, that means nuclear radius, and the last, nuclear density. Introduction. Earlier, we studied Rutherford scattering experiment and Bohr's model of atom, which explained how electrons orbit around the nucleus. Now, we focus on the nucleus itself, its composition, its properties, and classification. Constituents of nucleus. Aluminium 1327. In aluminium 1327, 13 means Z, that is atomic number. 27 means A, mass number. This we learned in our lower sections. Good. 13Z means there are 13 protons and 13 electrons. 27 minus 13 equals 14 means it gives you the neutron number. There are 14 neutrons. So here you have the aluminum nucleus surrounded by first orbit, second orbit, and third orbit. The first orbit contains 2 electrons, second orbit contains 8 electrons, totally 10. The remaining 3 electrons are in the third orbit. 1, 2, 3. Good. Now let us focus on nucleus. This nucleus contains 13 protons and 14 neutrons. Let us split. 5 plus 5 plus 3, 13 protons, and 5 plus 5 plus 4, you have 14 neutrons. Good. Let us first learn proton. It is positively charged particle. Its charge plus E equals 1.6 multiplied 10 power minus 19 coulomb, and the mass of the proton MP equals 1.6726 multiplied 10 power minus 27 kg. Mass of the proton is 1836 times mass of the electron. The electron mass is very negligible in atom. Let's learn neutron. It's a neutral particle. Its charge is 0. The mass of the neutron is 1.6749 multiplied 10 power minus 27 kg, slightly greater than mass of the proton. Protons plus neutrons together we call nucleons. Nucleon is a common name for proton and neutron. Important numbers. Atomic number Z. It gives you the number of protons in nucleus. Neutron number N. It gives you the number of neutrons in nucleus. Mass number A. This gives you total number of nucleons. A equals Z plus N. Representation of nucleus. General form is X, Z, A. X is the chemical symbol of the element, A is the mass number, and Z is the atomic number. Now, let us go with an example. Here we have nitrogen 715. X is N, which is the nitrogen. A is 15 nucleons. There are 15 nucleons. Z is 7. It gives you the number of protons. N equals A minus Z. 15 minus 7 gives you 8. 8 number of neutrons are available. 7 means it definitely represents nitrogen. So, N715 can also be written as N15. Charge of nucleus. Net charge equals plus Z times E due to protons. But in an atom, number of electrons equals number of protons. So, atom is electrically neutral. Isotopes. Atoms of the same element having the same number of protons, same Z, but different number of neutrons, different A, are called isotopes. Atoms of the same element having the same number of protons, same Z, but different number of neutrons, different A, are called isotopes. H11 hydrogen. Here we have one proton and one electron in the orbit. No neutron, one proton, zero neutron. Let us go for deuterium H12. Here in the nucleus there is one proton and one neutron and one electron is in the orbit. Therefore, one proton and one neutron. Let us go for tritium H13. One neutron, one proton. Addition to that, there is one more neutron. So, one proton, two neutron and one electron in the orbit. One proton and two neutrons. So, hydrogen, deuterium, tritium are the isotopes of hydrogen. Same Z, different N, so different A. Let's learn another example. Carbon 612. Here there are 6 protons, 12 minus 6 neutron. Here you have the nucleus of carbon where 1, 2, 3, 4, 5, 6. 6 protons and 1, 2, 3, 4, 5, 6. 6 neutrons. This is one of the isotopes of carbon. Let us go for carbon 613. Here we take carbon 612 nucleus, in that one neutron is added. So we get 6 protons and 7 neutrons. This is carbon 613. Next we have carbon 614. This is carbon 612. Here we add 2 neutrons. Therefore we get 6 protons and 8 neutrons. This is the third isotopes of carbon. In nature, carbon 612 is available 98.9% and carbon 13 available 1.1%. They are stable. Carbon 614 is radioactive. Same chemical properties, same electronic configuration. Isotopes are having same chemical property, that means they are having same electronic structure. Isotopes are different physical properties like mass, density, radioactivity. Third, isotopes placed in the same position in the periodic table. They are in the same position in the periodic table. In periodic table, isotopes are not having different places. Isobars. Atom of different elements having the same mass number A but different atomic numbers Z are called isobars. Atoms of different elements having same mass number but different atomic number are called isobars. Sulfur 1640. Here we have the nucleus with 16 protons and 24 neutrons. When we add these two, we get 14 nucleons. There are 16 number of electrons. So 16 protons and 24 neutrons. This is sulfur 1640. Let's go for chlorine 1740. In the nucleus of chlorine 1740, there are 17 protons and 23 neutrons. Together, they make 40 nucleons. In the orbit, there are 17 electrons. In chlorine 1740, 17 protons are available and 23 neutrons are available. Together, they are making 14 nucleons. Argon 1840. Here, in the nucleus of argon, there are 18 protons, 22 neutrons. Together, they make 40 nucleons. In the orbits, there are 18 electrons. So, 18 protons, 22 neutrons, together they make 40 nucleons in argon. So, all have 40 nucleons, but different protons and neutrons. So, this is what's called isobars. Same A, different Z. Isobar means same A, different Z. Let's learn key points. Isobars have different chemical and physical properties. Isobars have different chemical and physical properties. Isobars are different elements. Isobars are different elements. Isotones. Atoms of different elements having same number of neutrons, N, are called isotones. Atoms of different elements having the same number of neutrons, N, are called isotones. Let's go with example. First example is boron, 512. Here, 5 protons are there, 12 minus 5, 7 neutrons are there. So, in the nucleus of boron, 1, 2, 3, 4, 5, 6, 5 protons and 1, 2, 3, 4, 5, 6, 7. 7 neutrons are there. 5 protons and 7 neutrons. N is A minus Z equals 12 minus 5 equals 7 neutrons. Let's go for another example, carbon 613. Here there are 6 protons, 13 minus 6, 7 neutrons. Number of protons, 1, 2, 3, 4, 5, 6. Good. Number of neutron, 1, 2, 3, 4, 5, 6, 7. Good. So, 6 protons and 7 neutrons. Let's work on the number of neutrons. N equals A minus Z, that is 13 minus 6 equals 7 neutrons. So, both elements are having same number of neutrons, same N, but different Z and A. Atomic mass unit. Let's go with carbon 12, which contains 6 protons and 6 neutrons. Together, there are 12 nucleons. Good. In the first orbit, there are 2 electrons, and in the second orbit, there are 4 electrons. Together, there are 6 electrons. Mass of a nucleus is extremely small. They are in the order of 10 power minus 27 kg. So, we use a different unit to measure atomic masses, nuclear masses. It's called atomic mass unit, AMU. One atomic mass unit, 1 U equals 1 upon 12 multiply mass of 1 carbon 612 atom. The value is 1 atomic mass unit equals 1.660 multiply 10 power minus 27 kg. This value we use often in our problem. 1 atomic mass unit equals 1.660 multiply 10 power minus 27 kg. Masses in atomic mass unit. Particle mass. Proton. The mass of proton is 1.007276 U. The mass of neutron 1.008665 U. The neutron mass is slightly greater than mass of the proton. Then hydrogen atom. Hydrogen atom means we have to add the mass of the electron with the proton. So hydrogen atom contains one proton and one electron. So the mass of the hydrogen atom is 1.007825 U. Carbon 12 atom is simply 12 U. Given mass is usually atomic mass includes electron. To get nuclear mass, subtract mass of electrons. So nuclear mass equals atomic mass minus Z times mass of the electron. So to get nuclear mass, we have to subtract the total mass of the electron from atomic mass. Me is 9.1 multiplied 10 power minus 31 kg. The mass of the electron is 9.1 multiplied 10 power minus 31 kg. Mass measurement instrument. This is Bainbridge mass spectrometer. Atomic masses can be calculated from Bainbridge mass spectrometer. Average atomic mass of an element is weighed by isotopic abundance. Average atomic mass of an element is weighed by isotopic abundance. Size of the nucleus. This is radius of the nucleus. Here we have the atom and the atomic size is approximately 10 power minus 10 meter. Then the nuclear size is approximately 10 power minus 15 meter. Remember these two. If football is a nucleus, then the stadium would be the atom. Such a space is available inside the atom. Nucleus is extremely small, nearly spherical. Nuclear radius formula. It's an empirical formula, not derived formula. R equals R naught A power 1 upon 3. Here, the value of R naught is 1.2 Fermi. Fermi means 10 power minus 15 meter. R equals R naught A power 1 by 3. Let's learn nuclear density. For that, let's learn volume of the nucleus. V equals 4 upon 3 pi R cube. So, let us replace R as R naught A power 1 upon 3. Let us cube R. So, we get R cube equals R naught cube multiply A. Let us bring this value to the formula. So, we get V equals 4 upon 3 pi R naught cube A. Good. Let us learn mass of the nucleus, which is approximately A times mass of the proton. Good. Nuclear density rho equals mass of the nuclei divided by volume of the nuclei. Mass of the nuclei is A times mass of the proton. Volume of the nuclei is 4 upon 3 pi R naught cube A. Let's bring that into the picture. Rho equals A times MP divided by 4 by 3 pi R naught cube A. Here the A and A are getting cancelled. So the final formula for density, nuclear density, rho equals MP divided by 4 by 3 pi R naught cube. Good. The value is rho equals 2.3 multiply 10 power 17 kilogram per meter cube. The density of nucleus 2.3 multiply 10 power 17 kilogram per meter cube. Nuclear density is constant and independent of mass number. So the density equals MP divided by 4 by 3 pi R naught cube. The mass of the proton is constant, R naught is constant, the right hand side is totally constant, so the nuclear density is constant. So there is no A term on the right hand side of the formula, therefore nuclear density is independent of mass number. Nucleons are tightly packed. For an example, a teaspoon of nuclear matter would weigh a trillion tons. Remember that a teaspoon of nuclear matter would weigh a trillion tons. That's why the black hole are very heavy.